When we look up at night, we expect the quiet consistency of a solitary moon. It gives us a sense of security about our immediate cosmic neighborhood. But our orbit is actually quite crowded. Earth already has a small, rocky quasi-satellite wandering around it right now, proving our immediate space is far from empty. If a passing asteroid, roughly a kilometer wide, hits the exact right trajectory, it can be gravitationally trapped by our current moon. It becomes a submoon, a tiny companion to our primary satellite. This arrangement is temporary. The competing tidal forces from both Earth and the Moon pull the object in different directions, eventually destabilizing its orbit and sending a city-killing rock into our atmosphere at 72,000 kilometers per hour. This rogue asteroid provides a rare opportunity to study gravity and mass interactions in real time. The data collected from these impacts allows scientists to build the predictive models required to secure our future space-based infrastructure. To see the true power of these orbital mechanics, we have to scale up. Instead of a tiny asteroid, imagine a second moon, equal in size to our own, but orbiting at half the distance. Our coastal megacities are built around the predictability of the sea, but a massive new moon at half the distance would drag on our oceans with 8 times more force than we experience today, creating tides 300 meters high. Coastal infrastructure like this would be permanently submerged. These extreme tides would erase low-lying urban environments and force humanity into a rapid, chaotic migration inland. Grim. The destruction doesn't end at the shoreline. As the two moons slowly move away from Earth, they would eventually collide, sending a cataclysmic shower of debris down on whatever remains of our civilization. We cannot survive the addition of a second moon, but the physics of destruction become even more complex if the threat comes from Earth itself, specifically if our planet and its moon suddenly swapped sizes. In this scenario, Earth shrinks to the moon's volume, while the moon expands to match Earth. Because gravity depends on mass and radius, life changes instantly. Gravity drops to 27%, meaning a 70-kilogram person would weigh only 19 kilograms. This low-gravity environment offers massive logistical advantages. Aircraft launch with less fuel, and flights between major international hubs would take under 2 hours. However, our biology was never designed for this. Without the constant pull of 1G, our muscles would waste away, and fluids would migrate upward, resulting in a swollen face and weakened thin legs, a condition often called bird-leg syndrome. But the breakdown of the human body is a secondary concern. The sudden loss of planetary mass triggers a decay process that will make the entire surface of Earth completely uninhabitable. Little Earth no longer has the gravity to hold its atmosphere. Solar winds would quickly strip away our air. Internally, the smaller size causes the molten core to cool, shutting down Earth's magnetic field and removing our solar shield. The result is a scorched, irradiated rock. Without an atmosphere, oceans boil away, and the surface is sterilized by the sun's unshielded rays. Eventually, the giant new moon would slow our rotation until we become tidally locked. One day would last an entire month, trapping half the planet in a cycle of constant, freezing darkness. Life on Little Earth is a dead end. To survive, we would have to look toward the massive new moon as our only potential home in the solar system. Moving to the massive new moon is our only option, but it lacks a breathable atmosphere. Because it now has the gravity to hold one, we could use nuclear detonations to fracture the crust, releasing the immense volumes of trapped gases needed to build a new atmosphere. Once the atmosphere is established, we could extract the billions of tons of water ice frozen at the lunar poles. This would provide the raw materials for breathable oxygen and the creation of new oceans. While this scenario is a simulation, the technologies required to execute it are real. Observatories are already tracking these orbital variables to develop the survival strategies of the next century. Investment is already flowing into specific sectors, like low-gravity starship propulsion, asteroid detection systems, and automated lunar ice extraction, tools that are essential for long-term space settlement. Space-based technologies are becoming the new foundation of our global economy. Start investigating the opportunities in aerospace engineering and planetary defense, and subscribe for more breakdowns of the physics shaping our future. What threats do you think are still hiding in our shadow?